gives me great pleasure to introduce our speaker this evening, Dr. Graham Kent. Now, Graham is a research geophysicist, and he's the director of the SIO Visualization Center. He's also been a great friend and supporter of the Aquarium for a long time. And in fact, 2 years ago, he was a member of our external review panel where we were looking to see how we would develop the aquarium in the future. And also recently, he was a very important advisor for our present earthquake exhibit, which if you haven't seen it, I hope you'll have a look after this evening's lecture. He obtained his Bachelor of Science degree at San Diego State and his PhD here at Scripps Institution of Oceanography. However, all you really need to know about Graham is that he's one of the world's greatest reflection seismologists. Now, simply put, that means he collects images that allow him to see aspects of the world better than anyone else. For example, these images enabled him to see the western US breaking up and evolving over time. He has a 3D multi-channel image of a mid-ocean ridge. Now, many of you might think, okay, why is that important? Well, that enables us to see the structure of how the Earth's plates pull apart, actually at the very scale in which these processes work. So that basically means that we can see things better than we have before. And tonight's talk is going to show how this image data processing and acquisition really gives us a new twist on the California shear zone. So now, without any further ado, I'm going to ask Graham to talk this evening. And he is a little worried that some of his wonderful technology that he's brought here tonight won't work. But knowing Graham, I'm sure it's going to go wonderfully.
Many of you, I suspect maybe some investor types, looked at this, the title and said, I got to come here because there might be a lot of money to be had out in the Eastern California region. But the title of my talk today is California in 10 million years, beachfront property in the high Sierras. That's really not my title. That's what the Aquarium turned my title into. Right? The real title was, I guess California really will fall into the ocean. So with that, hopefully in the next 45 minutes, you will see how California will evolve in the next 10 million years. And again, I'm willing to bet anyone the best bottle of wine. We can show up over in Lone Pine. But really, the reason to understand this is that there are a lot of processes that are ongoing today along the eastern Sierras that in some ways you will appreciate through the photos if you've ever been there. But really, there are also natural hazards such as earthquakes and tsunamis that can occur today within the high Sierra, and they're related to this deeper seated process. So that's what I hope to show a little bit of tonight. But for those investment types, I just want to read this for you, that except for the geological information contained here, many of the matters discussed in this lecture are forward-looking statements that involve risks and uncertainties. So, this is a beautiful picture of, in the Bahia de Los Angeles area of the Gulf of California. And this is one of the less beautiful pictures that one might see along the eastern corridors of the Sierra heading out towards Tonopah. So I'll just give you a little outline of my talk and what I hope to bring across. One of the first things we'll do is just take a photo tour of this area. For many of you that have not been to the Gulf of California, the eastern side of the Sierras, it is certainly one of the most pretty places on the planet. And I've gotten some very famous photos from a number of people. And the one thing I'll tell you is there were no color filters used. There was no photoshopping. This is really, truly the way the land looks. And for instance, the high Sierra is also called the range of light because it's just spectacular under certain lighting conditions. The colors are just really surreal. So I just thought we'd get a better appreciation of what we're looking at. Then we're going to step back about 60, 70 million years and look what was going on with California and subduction along the west coast, and then go on to more modern rifting, and something that you're probably not familiar with, but by the end of the talk you will be, the development of the Walker Lane. We're going to do some 3D fly-throughs of some of the various data sets, right? And then we'll discuss a project that we've been working on for about 6 years here at Scripps, and looking at tsunami wave generation in Lake Tahoe. And lastly, we'll end with what we think California may look like in 10 million years. But before we go through this series of pictures of this rift system, I'm just going to talk about 3 different really types of faults that we study in this region. You're probably certainly now most familiar with this type of subduction thrusting events. This occurred obviously off of Sumatra, where one plate is pushed under another, and we now know the devastating consequences. And that's a thrusting or subduction type fault zone. If I had a Milky Way with me, I could pull the Milky Way apart, and that would basically highlight extension or normal faulting. We see a lot of that along the eastern edge of the Sierras. And lastly, we're all familiar with the San Andreas, and that's more of a strike-slip fault, like that. So these are the 3 types of faults that really have shaped California, or the Californias, both Baja and Alta, over the past 60 million years. But first I would like to just walk through some images of the rift zone. We're going to start in Lake Tahoe and work our way down to Cabo San Lucas. And again, I would like to thank John Paul Galleries and Mountain Light Gallery and the late Galen Rowell for these, some of these photos. They're absolutely spectacular. Many of you are familiar with Lake Tahoe. If you haven't been there, please go. It's absolutely lovely. But it's no different really than the rift lakes of Africa. In Africa, we're rifting older continent. But in California, we're rifting a younger Mesozoic or 60, 70 million year old piece of continental crust. So its expression is different, but it's really the same process that's going on. And as you know, Lake Tahoe is renowned for its water clarity, although it's stressed at this point due to development. Now we're looking from the north towards the south shore, and again, this is just beautiful, beautiful clear water. And this is certainly one of the prettiest pictures of Emerald Bay that I've ever seen. This is the second most photographed area in the United States. Only Niagara Falls, Kodak at least alleges, sees more photographs processed. And again, this is probably not your average day sunrise over Lake Tahoe. And again, we're going to head at the end of the talk, and again, Lake Tahoe is a rifted basin with large normal faults underneath about 500 meters of water, and that can cause a lot of problems. As we head south towards Mono Lake, and this is the Lake Galen Rowell's photo here, and the Tufa Towers in Mono Lake, as you're seeing, one of the things we keep seeing are lakes. And so even though we haven't quite developed the Gulf of California, Sea of Cortez, all the way up along the eastern Sierra, we do get these basins. And they're kind of the telltale signs of what's to come in the future. And again, this is a beautiful sunrise over Mono Lake. And we head a little bit further south in the Bishop area, and this is my favorite color picture I've ever seen in my life. The plants in the foreground are just surreal. And again, we're looking at one side of a rift where the normal fault, essentially extension, bounds up the Sierra Nevadas, and they've been rising over the 6, 7, 8 million years, and it's related to this rifting process. And lastly, we head into the Gulf of California region, and this is in the Loreto area, and again, beautiful area. Every corner that you turn is just it's just amazing. It's almost speechless. And lastly, many of you are familiar with Los Arcos in the Cabo San Lucas area. Interestingly enough, if you hang around these granites and then head across to Puerto Vallarta, in the southern part of town, you can see the same outcrop essentially. And that area's been rifted about 700 kilometers apart. So if you've been to enough of the beach communities in Mexico, you can start to see the geology on either side of the rift. But before that, what we'd like to do is just fly around this plate boundary and just get a sense of the larger geological picture. So this is a global perspective of North America. What we can do with a little bit of luck is fly in, flying here a lot quicker this time. This is a perspective of the North American and Pacific plate boundary, and as many of you know, the rifting, which started about 12 to 6 million years ago in the Gulf of California, there's a lot of small basins that are rifting apart, and the last transform fault, in fact, is the San Andreas that hooks back up to the Mendocino triple junction here. So we're going to study this system as well as the rift that's essentially propagating in the backside of the Sierras that will come back out just north of the Mendocino fracture zone. One of the things to realize over time, certainly 60, 70 million years ago, the whole area of the Californias was a subduction zone, very much like Sumatra, off Mexico, Japan, Chile. And so there was active subduction, very much like the Pacific Northwest, but essentially all the way along the Californias. And this plate that was subducting, called the Fairlawn plate, the ridge started getting closer and closer to the subduction zone. And that's a situation that's not very stable geologically, and ultimately ended up in this rifting event. So I'm going to switch back. And this is a beautiful cartoon that Dr. Tanya Otwater from University of California, Santa Barbara, just to highlight what subduction really is and what was going on during the Mesozoic, or about 70 million years ago at the end of the dinosaur age. And essentially we have the Fairlawn plate being shoved underneath North America, and of course we get heating and volcanism. This is very similar to what you see in the Pacific Northwest. This just as well could be Rainier, St. Helens, Hood, Three Sisters. But these string of volcanoes went all the way down along the Sierras and down into Mexico. And those volcanics that were not erupted, that solidified, are the granitic batholiths of the Sierras that we see today. Now, continents also grow in this manner. Occasionally there'll be another slice of continent or an arc volcano, and when it collides into this subduction zone trench, it just gets pasted, just gets shoved onto the continent. And that's how the western edge of the US continent, or North America, grew through time, just by accreting out these pieces of terrain, volcanoes, and continental crests. That's very complicated, so I have a different slide that might make it a little bit easier. So this is the Fairlawn cafeteria. This is courtesy of Jim Falls at UNR. And essentially, this is the subduction zone here, and the plates are coming over. And here are all the individual terrains, pieces of continent, volcanoes, and they all get essentially stacked in or accreted onto the edge of the continents. So I thought this is a much better way of showing how the California continental crust was created. And remember, please do not stack terrains, to be appreciated. Again, we're going to head and look at this process a number of times through this movie loop. And what we're going to see here is how this plate boundary interacted with the Californias over the last 40 million years, and we'll wait till it rewinds and starts over again. But recall that we have simple subduction along the Californias until the actual spreading center impinged onto Baja, California. And during that process, at about 12 million years down here, rifting was initiated along the Gulf of California, and the Sea of Cortez was formed, as well as the San Andreas Fault. And notice the Mendocino triple junction here migrating to the north. That will be an important part of the story. So we'll just go through it one more time. And really, when these ridges get close to the subduction zone, they actually die. It's very hard to subduct a ridge, for instance. And what we'll do now with the next slide is just come into the San Diego area and see what was happening just locally in our area. And the interesting thing is in some ways, since we have a San Diego State professor here, that San Diego State and UC Santa Barbara have always kind of party schools, right? Well, they both have their origin back in time, as we'll see with the next. See, Santa Barbara was very close to San Diego, and then it was finally rotated out as part of the transverse range. I can say that because I'm a San Diego State alum. One of the interesting things is that about 6-7 million years ago, a number of faults began to develop to the east of the San Andreas. Again, what's really happening is that the Pacific plate and the North American plate are kind of grinding by each other. And these are big plates, so they don't really care what's happening on the edges. And they're just going to find the easiest way to break. All right? And because of this big bow in the San Andreas, you know, in the LA region, it just kind of kicks out by Palm Springs and comes around through Mountain High and then back along the coast. That's just not a very happy state for a fault. It doesn't want to live that way. It's going to try to straighten itself out over time. And what we find out about the plate boundaries, and indeed, it is starting to straighten itself out. So the minute that, well, let me just back up. About 12 million years ago, there were San Andreas-like faults along the borderland of Baja, California. They're the Tosca, Rioja, San Benito faults. And these accommodate a lot of the slip between the Pacific plate and the North American plate. When it finally jumped inboard and most of that plate motion was taken up in the Gulf of California, this becomes a pretty peculiar geometry. And so it's now starting to break itself to the north. And this is the Garlock fault. This is the Eastern California shear zone. You might recognize Landers and Hector mine earthquakes back in the 90s. And this is the Owens Valley area, which potentially was the largest earthquake recorded in the contiguous 48 states historically. There's the Fort Tejon, there's the Owens Valley, 1872, and then there's the 1906. And depending on what textbook you look up, one of the three of them are the largest of the three earthquakes in the United States. One of the other interesting things, if you just look at volcanism for the last 15 million years, and this happens to be focused in the northern Sierras, it'll show you over the 15 million years, there's volcanism everywhere. But if we look in time, we notice that it's much more distributed, and as we count back in millions of years, geologists like big numbers, we can't deal with decades usually, it will basically sweep back, and that's basically showing us two processes that are ongoing. One of them is just the rifting that started, but more than that is that plate that was being subducted, it was being subducted, but once the subduction stopped, what happened to that plate? And it just sits there and essentially peels back, and they call it delamination. And as it peels back, essentially hot material comes in behind it, and that's where a lot of the volcanism is sourced. Many of you that have looked at a map of the basin and range, notice all these parallel ranges here, hence basin and range. And you go, that's a pretty interesting feature. This is basically when that plate peeled back away, the hot material rushed in and lifted this area up. And then this area was very high, and just the strength of the rocks wasn't able to hold it together, and it basically starts to spread out under its own gravitational body forces. And so this area of the basin and range is really showing us this delamination, uplift, and then basically collapse under its own gravitational body forces. The part that we're going to look more at for this talk is what's called the Walker Lane. And this is this shear zone along the eastern side of the Sierras, and we can count down from Tahoe, Honey Lake, Tahoe, Carson Valley, Long Valley, Owens Valley, Indian Wells, and this is the Eastern California shear zone, Mojave area. And essentially for the last 6 million years plus, the plate boundary has been trying to abandon the San Andreas and break its way through the Walker Lane. And what I really like about this one projection from Jeff Unruh, and it was published a few years ago in Geology, is it's the first projection that really allows you to see just how crazy the San Andreas Fault is. Basically, we're projecting so that the Sierra Nevada microplate, essentially this whole part of the Sierra Nevadas and some of the Great Valley, acts as just one solid plate. There's no faults in it. It's almost like a beam. And it's cruising off to the north in this projection. And as you see, as you come out of the Gulf of California, it would seem, at least common sense, it would be a lot easier to shear across this than to do this crazy jog through the San Andreas and then back around. And remember, this triple junction over time is going to continue to migrate along the coastline. So we're just looking at a process that's been ongoing for 6 million years, and over time, less and less slip is going to occur on the San Andreas and some of the faults to both the west and a few of the ones to the east, and it's going to break its way through. And we'll show you some evidence of how that's going to happen and why we know that. But I just thought this is a beautiful projection to see just, if you were a child and you wanted to rip a piece of paper, you're not going to rip it this way. You're going to try to just rip it straight through. It's a lot easier to do a straight tear than this crazy tear around this way. Now, many of you may have heard about the magnitude 6 earthquake in Parkfield in Central California about 4 or 5 months ago in September. This was an area where geophysicists and geologists said there's an earthquake every 30-some years. So what did we do? We went out and put instruments everywhere. And did it happen in 30 years? No. In fact, I think we could pretty much prevent earthquakes if we could put enough seismometers out. It finally came 14 years late. But the reason we like Parkfield is we pretty much lie through our teeth when we're teaching geology to the students. Because we talk about plates and how simple they are. There's these little plates and they're all distinct, and you draw lines on the chalkboard and pretty much you're lying, because the earth and geology is so much more complicated. But here is an example of an area where it's just simple. This is the perfect plate boundary. We're looking to the north now, and here's Paso Robles, to the north towards the Bay Area, and this is the trace of the San Andreas right through the Parkfield area. And the thing I want you to remember this in your mind, and we're going to go to Southern California in a few minutes, and it's going to be a mess. But in this area, it's perfect. And the big diamond that's red is the main shock. The purple ones that are a little bit smaller are the aftershocks within about a day, and then you'll see the earthquake since. And they're going to basically map out the fault plane. Now look at this. You know, we're talking about that perfect plate, and you can kind of spin around. See how it just, everything lines up on an edge? And that's because this is one of the few perfect plate boundaries that we have. This is not typical. See how it just lines up on an edge? So this is something that we like to teach, but we don't see very often. We can kind of back up, and looks like the coffee over there was pretty effective. But now what we're going to do is we're going to run over to the imperfect plate boundary, and we're going to look at Southern California, where we are right now. So we're now back in SoCal. Let's sweep away and back up just a little bit. One of the things that you'll notice is, unlike Parkfield, these kind of copper lines showing fault lines, there's just tons of them. And we know that there's the San Andreas and the San Jacinto and the Elsinore Fault. We have the Rose Canyon Fault just about a mile offshore here. And then there's the Coronado Banks Fault and the San Clemente Fault. There's a lot of faults that help basically translate the Pacific past North America. It's not just on one fault. And certainly in Southern California, it's a pretty wide band. These two faults up here are the Landers series of earthquakes and the Hector mine. This is 92 and 99. There's also it was the Halloween earthquake about 5 years ago on the San Jacinto fault. And we're going to fly underneath. And remember how edge-on the earthquakes were in Central California? Well, this is not the case here. They're much more like clouds. You don't really, if I just rotate around, we really don't see a plane. They just look like clouds. It's much more diffuse. At best, we kind of get a plane about right there. Now we're going to swing over towards and again, we're going to map out. This is part of the Eastern California shear zone, Landers and Hector mine faults. And they're going to basically, there's these series of dextral or right lateral faults. Here's the Garlock fault coming across, Owens Valley, Death Valley, kick up there. So again, as the San Andreas becomes further abandoned by not only its arcuate shape, but this Mendocino triple junction, it's easier to break through and cut the crust this way, okay? And again, it's when you do some tricks with tearing paper, you know, sometimes it goes where it wants to go, not where you want it to go. And this is the same idea, except we're looking at a continental scale. All right, and the last thing in this little fly through, we're going to go head to the south and look at the Gulf of California. And some of these results are from an experiment that we had back in 2002 where we were looking at the development of this rift zone. And what's really neat about studying this rift zone is you can actually really study both sides of the rift. If you can imagine, if you're studying the Atlantic and you look at, let's say, off Virginia, you have to go all the way off to Africa and everything in between, and then how do you line up those pieces? So it's a lot easier to line up the various conjugate pieces in the Gulf of California. And there's any number of different data sets. On land, we have the local geology painted over the digital elevation maps. And offshore, we have both the global topography set, and if we can look closer, we have Professor Peter Lonsdale's bathymetry. And this little basin here called the Alarcon Basin is really the first basin within the Gulf of California where it started out as a continent and it rifted until more and more and stretched more until finally you had ocean floor being created. And we can see the abyssal hills now in the Alarcon Basin. And if we rotate and look underneath, we can look at our, in this case it's a velocity model. We just gotta pop underneath. Whoops. I'll back out a little bit. Well, we can see through it. How about that? Not so much, huh? All right, let's try one more time. There we go. Kind of got it. But this is basically looking in depth at crust in the Alarcon Basin, which is about 6 kilometers. And then as you head further away, it gets thicker and thicker and thicker. And this is just a progressive thinning and stretching. If I took that Milky Way and kept pulling it and pulling it and pulling it, it would finally just thin down to the point where it would just disappear. And essentially at that point, what we've gone to is more of a conventional mid-ocean ridge. All right, so now the last part of the talk, we're going to look at the Tahoe area, which is really where we've been doing most of our research. And so I think this whole process of rifting along the eastern side of the Sierras really didn't come into fashion until just the last few years. One of the things we looked at was, we knew that if you were, I guess Monty was skiing over in Utah, so when he was over at Alta, and let's say I was skiing at Lake Tahoe, we know that on average, the two ski resorts separate by about 1.2 centimeters a year, about that much, every year, right? Which is not a lot, considering that San Andreas fault slips about 2 to 3 times that, but it's every year. Well, what we mistakenly thought was that that slip was distributed across the entire basin and range. Because heck, if you just look at it, there's all these hills, they go up and down and up and down and up and down and up and down until you hit the Sierra. So obviously you take this distance, you divide by 1.2, and that's how the Earth works. Well, it wasn't. What we found out was about 2 millimeters a year occurred right on the Wasatch Fault. And from the Wasatch Fault until we almost got to the eastern front of the Sierras, this was mostly just a push. Extended a little bit, some pushed up a little bit, and then boom, once we hit this region of the Walker Lane, that's where we got basically 10 millimeters of the 12 millimeters of extension or slip in this very narrow zone. Now, a lot of you have that GPS unit in your car, right? And that's a cheap version of the GPS unit. Folks who have a lot more money can use a special GPS unit that's capable with all the processing of an accuracy of about 1 millimeter. All right? So they put all these GPS stations along the basin and range on this US 50 transect. You might have recognized that shape there. And imagine that if I'm at Alta and I move over to this station, if we're basically in lock and step and we're not separating, this arrow length is going to be 0, and this is going to be just an itty bitty little bit more. That's how much I've moved. If I move a lot further away, that arrow becomes a lot bigger, okay? So as you see, the arrows are not really that long until you finally get over to the Walker Lane, and then they just bust out. And what it's showing is, by and large, you're not really rifting or stretching this area too much until you hit the Walker Lane, and then this stuff just goes crazy. So right in this area, the plate's shifting up about 10 millimeters a year. And so that was something that we didn't know until about 5 years ago, which coincidentally happened to be the time that we started looking at faulting in Lake Tahoe. And this part of the talk is both to understand exactly how faulting works in the Lake Tahoe region, and to also realize that there's a hazard there that's a little bit peculiar. And now you probably understand why by looking. I think we're all heightened to that awareness now after the Boxing Day tsunami. And here's what you'd like to do. If I have a fault that I want to study, right, and understand the history of earthquakes on that fault, I'm going to dig a big old trench. And this is actually on the smallest of the 3 faults in Lake Tahoe. And this is Gordon Seitz from San Diego State, another Monty Marshall student. And we went up there this past summer and dug this trench. It's about 8 meters deep. It's kind of scary and not very wide. And what we do is we expose the history of the faulting, namely that you tend to have layers, and when the layers are disrupted, you can basically see an individual event, earthquake event. And so what you want to do is make a big deep cut and then look on the face of the wall and realize that there's all these different events, and it's kind of like a puzzle. I always say it's a bit like CSI for rock jocks, right? It's a little bit of that crime scene investigation, but you're trying to back out, and actually you can see all this coarse grained material here. This is called a colluvial wedge, and what happens is right when you get a rupture, it might be 2-3 meters, about 10 foot high, it just boom, it's down 10 feet. And all the stuff during that movement and over the next few years, all this rubble that was used to be sitting on top collapses into this wedge or colluvial wedge. And this tells us how big the last earthquake was. And then we go in and get carbon samples or other dating techniques, and we can piece together a time history. And what you want to do over time is understand when the last, say, 5, 6, 7, 8, 9, 10 earthquakes are or were, and then understand their time history so you can forecast. I didn't say predict. You can forecast when the next earthquake is or will be. And they've only really done that for about 4 or 5 faults in the United States, like the San Jacinto, San Andreas, Wasatch faults, for example. So in Tahoe, we're trying to do that because when these faults rupture, there's significant consequences. But guess what? The 2 major faults in the basin are underneath 500 meters of water. So I do not know very many backhoes that are capable of going to 500 meters. And more importantly, I can't hold my breath that long. And so we're kind of stuck because, think of this, you have these very dangerous faults that are able to generate tsunamis, but they're underwater, so our conventional techniques don't work. So that seems like a project that we should spend some time on. And we started this in '99, and that was a year after the 1998 Papua New Guinea tsunami that killed about 2,500 people. And at that time we thought, hey, now people understand how dangerous these things are. And as we know now, that was just kind of foretold what would happen in the future. And this is just to let you know that when you get involved with these big projects, there's people from all over the country. And this is about 10 or 12 people that have been involved with this project over the last 5 or 6 years. Now, why is it important? We'll loop through this movie a few times, but this is a tsunami wave cruising across Lake Tahoe, and this is the time in seconds. Right there it says 84 seconds, 98 seconds, 2 minutes. So, oh my God, we're already across the lake in 2 minutes. And we're going to hit about 3 minutes here. We're going to hit Incline Village in about 3 minutes. This was modeled by Dr. John Anderson and his student, Glenn Inchinose, and he's at UNR now. Used to work at Scripps as well. And this is a magnitude 7 event along the West Tahoe Fault and about 2 3/4 meters average slip, which you'll see is actually probably conservative. And if you were looking at this depth scale, and when we first started the tsunami, realizing that if you saw those colors, anywhere around the lake, the peak wave heights were between 3 and 10 meters, depending on whether you ruptured the West Tahoe or the State Line Fault, and where you are versus all the bathymetry and stuff. Now, just to recall, the highest wave heights that I've heard recorded for the Boxing Day tsunami near Banda Aceh were 14 meters. The waves that destroyed in the Sri Lanka, Phuket Island areas were 4 to 10 meters, but closer to 4 meters. So a garden variety normal faulting event in Lake Tahoe basically can generate waves that are equivalent to what we saw on the Boxing Day event. But just because I have a model doesn't mean it will happen, right? And so that's the real question. Does this happen every 1,000 years, every 50,000 years, every million years? If it's every million years, it's like getting hit by a meteor, so what? If it happens every 1,000 years, then that's a big deal, because it may have not happened for 1,000 years, and so you're sitting on a time bomb. So what we went out is to try to put real numbers on the slip rates of the faults and how often they reoccurred. And so how do we do that? And Professor Neil Driscoll in GRD, Geological Research Division, developed this system, which I always called it acoustic trencher. It's really called a seismic chirp, but the way I like to think of it is it's making that trench that you do in paleoseismology, but you make it with sound. And so what we did here is took 3 different types of data. This is the Scripps chirp. This is if you got some moolah and you want to buy off the shelf technology. And this is what they collected back in the 80s and 90s, and there's lots of this. Now, believe it or not, this is the same area off the coast of South Carolina. So this is a lot of data, old Huntec boomer data. It's yucky. This stuff, you almost start getting a sense of what the geology is, right? But is this a channel, or I don't know. But as you can see, when you compare this picture with that picture, it's kind of night and day. The resolution's about a decimeter, about somewhere around here. So we're really starting to get to the level that's important for paleoseismology. Like, we can start resolving individual events in the seismic data, all right? And we can start really understanding geology. And we'd like to say this is the difference between interpreting and guessing and knowing. And so we were able to take this technology up to Lake Tahoe and do some really groundbreaking science with it. And I think this underscores one of the functions of Scripps and a few of the other oceanographic institutions, is that we still develop instruments. And it's through the instrument development that we can make breakthroughs. You know, a lot of companies use this and buy this technology, but they don't have really access to this until we develop the fourth panel and this becomes the standard off-the-shelf technology. So that's, again, an important reminder of why it's important for institutions like Scripps to be around. And here's this being deployed off of the RV Jean LeConte. We work closely with a number of institutions, as you saw, including University of California, Davis, and Charles Goldman's group. And I'll tell you, it was tough work for the last 5 or 6 years in Tahoe, but somebody had to do it. And unlike today, within the UNOLS fleet, the university fleet, you can't swim call, right? Well, guess what? On the Jean LeConte, when it gets hot and you're tired, you get to jump into the water, so that's always a pleasure. But this instrument is different in a number of ways, and it's the transducer array that makes the chirp sound. It kind of goes whoop, 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 8 times a second. And we can signal process that chirp into a very resolute wavelet. And we also do all the digitization on the fish itself. And believe it or not, those two things are the difference between the middle panel and the top panel. And we're now proposing to do the fourth panel, where we're going to be able to do the next step. We're going to get down to even further resolutions. And this is what we need to do to further our science. And now we're going to flip back over to Lake Tahoe, and we're going to understand how we reconstructed the fault slip history in the Tahoe region, if I can keep my flying under control. All right. This data was, the bathymetric data that you see here was collected in 1998 by James Gardner at the USGS. And what we've integrated here in this, what we call a visualization scene, is about 5 or 6 different data types. The deeper bathymetric data in the lake, kind of from the yellows and greens down to these purples, were collected with typical sonar acoustic multi-beam bathymetry. The shallow areas, however, are collected with a LiDAR. Lake Tahoe is clear enough that you can actually scan a laser through the water and get the shallowest levels of the lake in exquisite detail. Then on land, this is your typical 7.5 minute quadrangle USGS digital elevation map, which means if you've ever went backpacking on these things, if you follow them too literally, you could step off a cliff. So you don't, they're not the greatest maps in the world, but they'll do. Again, what we do is collect these little acoustic trenches with the chirp device. Now I want to back up, and what we were talking about with this modeling a few minutes ago were hypothetical ruptures along the West Tahoe and state line faults. And we'll fly around and look at these escarpments from the faults. Remember, if you see ground rupture on an earthquake, especially a normal fault, that means it's very large 6, low 7 minimum. So we're not in the case where, okay, you guys are exaggerating, it's a whole bunch of magnitude 4 events, and you're just making it bigger than it really is. But in fact, we know once we get these significant fault scarps that rupture the land, that they're biggies. They don't break small. The other interesting thing in talking about a really bad day is, notice these blocks here? This one's not quite as big as Soledad, Mount Soledad, but it's kind of on the same order. See this big block? If you stare at this long enough, it wants to creep up over here, and this block creeps up there. This little guy shoves in over here, and you can play the game and realize that this pile of little icebergs almost belong back in this McKinney Bay, or the McKinney Bay reentrant. And in fact, about 50,000 years ago, this edge of Tahoe collapsed and generated this huge slide. Now, the tsunami height from this event has been estimated to be 100 meters. Okay? So that's 300 and some feet, and that doesn't include run-up, which certainly probably spilled over the top of the mountains. There was an event in Latilla Bay in the 50s by Glacier Bay where a similar sized earthquake-triggered landslide generated, now get ready for this, a run-up of 1,700 feet, all right, and took down trees that were like this big. All right, so this was a very bad day. Now, this may happen again. If you shake this basin enough, you can see these very steep sides over here by Rubicon, over here by Crystal Bay. It may be winning the geolottery. It doesn't happen that often. Maybe every 50,000 years, 100,000 years. But one has to realize that there is the potential of just an astronomical failure and devastation of the Tahoe area that goes beyond anything that we can even comprehend. But let's first step back from that and worry about the one that's more realistic, at least in the short term, and that's looking at the ruptures of these different normal faults. So we're going to fly down to the state line fault right here, and I'm going to look at this screen so I can fly. What we really liked about working in the Tahoe area is pretty much every time we collected another profile, we could stick it into a textbook because the geology was so straightforward. Here's the Fault Scarp, which in and of itself was about 40-some feet high, and if we drained all the water out, there'd probably be a little sign that said the great earthquake of 4000 BC was here, right? You know, but it's again under 500 meters of water. Now, remember that big catastrophic landslide about 50,000 years ago? Well, since that time and through a number of glacial episodes, the lake sediments just rained out, suspension sediments, and produced about a 20-some meter thick pile of sediments on top of this slide. A little bit thinner on this top, and here's the top of the slide. And guess what? These two sides don't match. And they don't match because they cross the state line fault. And let's just rotate under a little bit. Now, if I were to take my acoustic ruler out and measure from this point here to this point there, it's 21 meters. So we now know that in 50,000 years that this surface has been split by anywhere from 21 to 25 meters. That's a lot, right? But that's not our only clue to what's going on. If we fly back and look at the edge of Lake Tahoe, if you're familiar, we're going to head over towards Emerald Bay and Rubicon. This is a profile that's showing us the telltale signs of an old paleo shoreline terrace. Now, a lot of you, when you were kids, or your kids today, they get all filthy and they jump in a bathtub and they play around and they jump out, and then things kind of settle and then you drain and you leave a bathtub ring. Well, very similar in Lake Tahoe area, from about 60,000 years till 20,000 years, the lake level was about 15 meters lower. And it just sat there and the wave action cut these beautiful benches out. And then the last glacial maximum came through, raised the lake level up, the channel filled in, and voila, we have the current lake level. But this surface was then preserved. So every time this surface was intersected by a fault, and then the fault would drop down to the east, that was preserved. It was no longer beveled off. And so now we just encircle the lake, and every time we cross the fault, we get to see this bathtub ring, or this old shoreline, jump up as we go counterclockwise. And so this is a real neat little trick. And so if we look in this area on the west side, and basically right very near the West Tahoe Fault, this shoreline here is at 11 meters. See that little blivet right there? That's about the distance from my son's hind end to the floor. About the height of your chair, the seat in your chair. So this is very high resolution data. And you can see how deformed the sediments are. In the past, this area certainly was being affected by the West Tahoe Fault. Now we're going to fly across the lake to Cave Rock. And many of you have probably driven through Cave Rock on your way to helping the casinos build larger buildings. So we're going to cruise into Cave Rock. And we'll look at the shoreline on this side of the lake. Here we go. Here's the old erosional terrace. You can see how these beds are truncated off. And then here's the modern delta deposits prograding out on top of it. And at this level right here, it's 21 meters or 10 meters. So about 3 years ago, we took a big barge, 80-some foot barge, and we rented a big old 40-foot crane. And then we told UC people who self-insure that this is what we're going to do. And there were some high winds. We almost lost the whole kit and caboodle. So, you know, thanks UC. One of these times we're not going to come back with our gear and they're going to be stuck with it. But for now, we were able to collect some very critical data, and we were able to age date the surface at about 19,000 years. Kind of makes sense because that's when the glaciers were again big. And if you're familiar with Squaw Valley, that's where the Olympics were in 1960, but a big glacier came out, abutted the valley there, and rose the lake with an ice dam. So now if we're going to head back and we're going to fly down to the Ponderosa Ranch. I think a lot of you are familiar with that, right? Little Joe and Ben and Haas, right? Well, right outside their front doorstep, believe it or not, is another terrace here. And this terrace is at about 26, 27 meters, or another 5 meters deeper. So envision this. You're having a picnic with your family 20,000 years ago at Emerald Bay, and one of you decide to walk over to Incline Village, and then you wait there for 20,000 years. All right, it's a long picnic day. Your family member will now be 50 feet lower, or about 15 to 16 meters lower to the northeast due to fault movement on the West Tahoe, the state line, and the Incline Village. So you think about 50 feet, your average rupture might be something on order of about 10 feet. That takes a lot of large earthquakes to drop one shoreline down 50 feet in 20,000 years. And these are the telltale signs that there's very much earthquake activity in the Tahoe Basin, and it's ongoing. In fact, we started to look around. Once we saw everything underneath the water, we started looking above the water. And again, as a kid, we used to drive through there and ask our parents to honk the horn through the cave at Cave Rock. And in fact, the cave at Cave Rock that you drive through is man-made, but right up here is a beautiful wave-cut cave. And we knew there was a cave on the other side of the lake, and they were likely formed when Lake Tahoe was a lot higher during Tahoe glaciation 60,000 years ago. So we said, we know in 20,000 years it's 10 meters deeper or lower to the east. So maybe in 60,000 years this cave should be about 3 times as much, right? And so what we did are about 30 meters. So I had a student who unfortunately, maybe that's not the right word, but had to go over and fight in Iraq for a year. So he came back to Scripps and we said, well, what should we do? So we sent him skiing up in Lake Tahoe, but said, if you're going to get to ski, you have to first go measure those caves, and then you can ski. So that was him reacclimating to college life. And so Jeff went up there, and lo and behold, it was almost too good to be true. It was 29.7 meters between the different caves. And so what does this all mean with regards to the Tahoe area? Essentially, we have 3 major fault zones, 2 of which are underwater. And they have slip rates that are slightly less than 1 millimeter per year along the West Tahoe, along the state line, Incline Village. And this is where we basically, you saw the trench a little earlier. Now, if they basically rupture in a uniform manner, like West Tahoe goes, and then a certain amount of time the state line goes, and the West Tahoe goes again, equally spread out, they don't have to be that way. They can cluster together. Every 3,000 years, you will get a tsunami that will be on the order that you saw modeled, with wave heights from 3 to 10 meters. And so the real question now is when was the last one? And that's what we're working on. But it also demonstrates just how active the Tahoe Basin is and how it's being rifted apart. And so it basically is a manifestation of what's going to happen for the next 10 million years. And one of the reasons to do it, of course, and what I didn't show you was that trench that we dug was 30 feet from the Incline Village Elementary School, which is a cinder block building with 600 kids a day, literally built right on top of the Incline Village Fault, which you can't hold us to it, but it looks like the last major event was about 600 years ago. So that's kind of scary, and but important also. So what's California going to look like in 10 million years? Well, one of the things I hope is the menu gets a lot better, because I like the tacos de pescado and camarón, carne asada, right? Chorizo, machaca, much better. And along with that new menu, we're probably going to see something, if Baja was any kind of as a guide of what's going to happen with the San Andreas, is over the next 10 million years, you're going to see progressively more and more slip be transferred over to the Walker Lane. And in a way, again, very analogous to what happened to Baja. And if this scenario, which is more or less what's likely to happen, then you'll accumulate about 500 kilometers of dextral slip and extension within the Walker Lane. And so, depending on how the faults break, you'll start developing these small basins like they did in the Gulf of California. And once they kind of spread out enough, they'll interconnect. And what we'll see is the Sea of Cortez starting to extend up towards Tahoe and Honey Lake. And it should be an interesting sight. And unfortunately, we're not going to be there. But I think it does give us an appreciation for the beauty of the area and why you see these beautiful rifted mountains, why on occasion you might see a volcanic event in Mammoth, or why potentially there might even be a tsunami in Lake Tahoe, or when the tsunami occurs, you'll understand why that's occurring. And again, I'd like to thank you for coming on Valentine's Day, and hope you get a little better appreciation for the Californias and how they're going to evolve over the next 10 million years. So thank you.